Hi, welcome to our second meetup of the month dedicated to machine learning tools, and thank you so much for joining us. So, as usual, we will have 1 hour of meetup, and the first 45 minutes will be dedicated to the talk, and we'll have 15 minutes in the end for Q&A. So please post your questions in the YouTube chat so we can collect them and ask them in the end. So today we are happy to have Jiri Borovec. Jiri is a senior researcher engineer at Grid AI, and he works primarily in the fields of machine learning and data science. He is particularly interested in exploring and solving problems using novel approaches to machine learning. He has developed several open source Python packages, is a core contributor to PyTorch Lightning and Torch metrics, and actively participates in a handful of other innovative projects. So without further ado, welcome, Jiri.
Hello and welcome. So let me start with the presentation. So slideshow. Hope that now you see the screen as I do. So during the presentation, so I want to go with PyTorch Lightning presenting to you. And let's start from some short introduction about deep learning, even you hear it all the time, I believe. But I think it's important to understand what's the value of PyTorch Lightning. So as I was introduced, so I'm a research engineer on Grid and Lightning, and you can catch me on Twitter or GitHub. This is pretty much what was already mentioned. Just at the bottom, as those slides will be shared with you later. So I'm putting a reference for a series of blog posts which are related to this presentation. And so what can you expect from this presentation? So I will start with some, let's say, general introduction what deep learning machine learning is, just to get you up to the speed. Then we will talk about some short, realistic, real-world examples. And then I will use later also some Kaggle competitions. In particular, it will be Plant Pathology from last year. Then we will talk about deep learning components and flows. What are the principles? Just small repetition, just to introduce what's the value of framework PyTorch Lightning. And that will be about like first 15 minutes. And then I would like to spend most of the time on showcasing the Kaggle competition with Lightning and eventually with Flash, and going through the code base, which I have prepared, and running the code in a live session. And in the end, we will keep some time for discussion and questions if you are interested. So there's the standard dilemma: what's the relation between machine learning, AI, and deep learning? I found that it's not always well described, and some people may have different opinion. But I'm quite aligned with this schema, which says that AI is the, let's say, widest range of techniques and solving problems. Then subset is machine learning, and then even smaller subset of machine learning is deep learning, because it's specific to a specific family of models. And then, as you may hear from broadcasting of job posting, so there's always looking for data scientists, which is kind of cross between all those three, and also adding some statistics and visualization, as you need to solve and bring a real value to the company. In general, the machine learning can be divided into three and then subdivided to multiple domains, eventually tasks. So in principle, it's supervised, unsupervised learning, and then reinforcement learning. Unsupervised learning, it's, for example, some clustering if you don't know anything about the data and you need to find some meaning. Or, for example, PCA could be some dimension reduction, which is usually also unsupervised. Then what we are going to talk in this part is supervised learning, when you have example of classification on a regression, but basically you have some training data. So you know what is the input and what's the expected output of the model, or even if you put it to a human, so what are the true answers. And then based off this pairing between the inputs as raw data and expected output, we are trying to optimize some, let's say, black box in this session to give us the best output, best results according to metric we measure. So, for example, for classification, we can measure some F1 score, which is balanced accuracy and precision. Or for regression, we can measure, for example, some mean square error or any other metric. And just for simplicity, I will completely skip the reinforcement learning as this family on its own. So talking about some examples as classification or those tasks are nice to hear, but it's good always to have some concrete idea what it can cover and what it means. So as I am coming from computer vision, so I will illustrate some of those real world tasks on computer vision mainly. So when we have input image, so one of the initial tasks or simple task is semantic segmentation, when we want to classify each in each pixel in the picture where it belongs. So for example, if it's a cat, grass, or trees, or sky, then we can see it also as an increased difficulty of the task. So the next level would be classification and localization, which is also the standard object detection. When well, in this case, it's just one object in the scene. So you need to identify the object, then you also classify, then you have the object detection when you assume that you have multiple objects and can be overlapped. And then let's say the hardest task in this sequence is instant segmentation, when you also combine the contour of each, when you want to detect contour of each object, and then have a very fine object localization within the scene. Some other recent, well, they are not much recent anymore, they are already a year or a bit longer. So you can also detect some skeleton of people doing some activities, which is important, which can be useful for discovering the activity or classifying the activity. So, for example, playing golf, walking, or playing baseball. Then last year there was quite popular clip algorithm, which was according the text description, it was generating images which were not part of the database. So it was considered as a partially creative task. And one of those examples is that the algorithm was asked to give us some images of avocado chair. So you see how they put it together. Then if we go a bit out of the computer vision, so for NLP, the standard or very common task is chatbot, which is answering questions. Usually you need to create some database of knowledge and then try to mimic a human agent on the other hand, and answering the standard questions from a forum or from documentation or any other source of information of knowledge. And on the top right, so we have also the regression, as mentioned before, which could be useful, for example, for predicting stock markets or weather forecasting or outages of electricity. So what the deep learning is, I like quite this picture because it's kind of, that explains how different people see us and how we see among us. So everyone thinks that the deep learning is something almost human, you can solve everything. Then friends thinks that you are connected to the motherboard and solving the task. But I like then what I think that I'm superhuman and smart as Jan LeCun, but in the end, in many cases, you are importing just some of those good libraries like TensorFlow, PyTorch, Keras, PyTorch Lightning, or anything, and then you just use it. So not many people really knows what's behind the math, and that could be danger in the end. So coming, as we specify the deep learning cycle, so for the, well, it can be seen as any machine learning model training. So there are some specific for deep learning, but in principle, this is very similar for any. So at the beginning, you have some data, input data, which could be images of cat and dogs. and also they need to be paired with annotation. So we need to say that this picture is cat, this picture is a dog. Then you are shuffling those data to two subsets. In ideally, you would be creating three subsets. So it will be training, validation, and testing. The testing is always taken apart and shouldn't have any leakage to the training, eventually validation dataset. But for simplicity, just keep now the training and validation. And then as deep learning is nowadays still using mostly some gradient descent methods or any variation of those. So it's working in loops. So that's one of the one of the key aspects of the deep learning. So the loop is composed from training loop and validation loop. So the training loop is computing gradients for the weights of the model, which needs to be updated, and then the validation loop is evaluating what's the performance of the actual train state of the train model on the validation dataset. This is rather important, especially if you want to prevent overfitting on the training data. So that's something which would be not welcome, and also it can very much lower the generalization capability of your model. So in practice, it would mean that you train model on cat and dogs, but it will be only to distinguish between dogs which are black and cats which are white. And that's not the case which we want to achieve. So coming back to the training loop, so deep learning has, let's say, some specific parts, which is a bit different from standard machine learning models like random forest, SVN, or those. And some of them are, for example, checkpointing. You want to save your model time to time, don't to wait for the end because it takes very long and you'll be wasting resources if it accidentally fall in middle. Then profiling, if you want to optimize your training, so you can find if you have, let's say, some slow data loading, or if some augmentation is taking much longer. What's very interesting is mix precision, which gives you, because there are some papers and there is research that not for all numbers in the deep model, especially for the gradients, you need full float precision. So you can mix it with 16 float 16, and you still be reaching very similar results as with the full one. And that's what's usually bothering many people. It's proper moving the data and model between devices, especially if you are working with GPU, TPU, IPU, any other accelerator. So just making mistake in this part would cost you quite a lot of time to discover why it doesn't compute or converge as you want. And in the end, you have the trained model, and you would to enter a new data and get the prediction. So at the top, you would pass picture of cat and dog, and you want to know, okay, that the output is that there is a one cat and one dog. So mentioned earlier, there are many frameworks you can use, and but I would still say that nowadays one of the mainstream are TensorFlow and PyTorch. The other could be nice, and I don't have any other opinion about them. I haven't tried them. But we can also see that there are, let's say, different level of abstraction. So for example, for TensorFlow, it's Keras. For PyTorch, we do the similar abstraction. But for me, the advantage of PyTorch Lightning is that the abstraction is rather linear. So you can decide how much you want to stay with the default workflow and parameters in PyTorch Lightning, and how much you want to customize it and hands-on and going deeper to PyTorch itself. So what's PyTorch Lightning? I like this schema from different publication, and I think that it's a nice interpretation what it means. So PyTorch Lightning is, in simple words, just good good structure to your codes, coding the best deep learning and machine learning practices. So you can easily share the code and everyone will understand what you are doing because it's kind of standardized. And in this fashion, so you are taking care about data, about model, about forward pass, which is defining how the data are fed to the model, then optimization and the training step, which is also how if you are adding metrics or any other procedure on the training. And then what's abstracted out is a trainer, which does all the hard work for you. So as I mentioned, checkpointing, logging, moving to proper devices, metric handling, or anything which is kind of the boring part for many data scientists. Here we have a short visualization. I will go later with animation. So at the on the left side, so the gray code is all you have at the beginning with PyTorch. And then if you move to PyTorch Lightning, or ideally if you start with PyTorch Lightning, so you are separating the Lightning module, which is about the model and how you train your model. So training logic, so the training step, validation step, test step, eventually some other configurations. And then you have your data part. So you also separate what's the data logic. So eventually you can easily then pass one of your colleague the Lightning module, which is about the model, or you can, for your own experimentation, have one Lightning module and then just switch different data set, for example, from flowers classification to cat and dogs classification. So you will be just changing the data module. And on the right side, so it's schematic how the simplification works. So from your original code, you have your network, which stays the same. But then when we come to the training loop, so it you see that almost all the boilerplate, like iterating over epoch, iterating over batches, then moving to the device, then handling the backward update, then step of the optimizer, and anything else is abstracted to the trainer. So you don't need to you don't need to think about it. And the good part is that as many people use it, so you can believe that it's well tested compared to writing own code base for each task. It's easily to make a mistake. So coming to the animation, so the first step when we have our code, so we move the model declaration to the Lightning model. In this case, it's autoencoder. And we still keep the part about moving to device at this moment. So then we define the forward pass, also configure optimizers. Then we are defining the training step, which says that we have the input batch of training data and annotation. Again, moving to device, viewing, then we compute the predictions, loss, and send it back. And also we add the validation step. So we want to be sure that we know that we also track the performance on the validation data set. So we don't diverge from the training, don't overfit the train data. Now, when we introduce the trainer, so we can remove the moving to device because it's handled by trainer. We also can remove the loss backward and optimizer step as it is also handled in the trainer. So now we have the Lightning autoencoder. So we can import it as a one object of this class. Well, we create this object. Then we create a trainer, which is given to us from the Lightning. And then you just call trainer fit my model on my data set. And that's all what you do. Then with this simplification, you can easily just put there how many GPUs you want to use, or if you want to work with TPUs or anything else. So that's about the general introduction and brief introduction to Lightning. But I think that what's more valuable is the plant pathology, which is image classification. It's multi-label image classification on apple leaves, and the task is to discover some diseases. So there are 6 different diseases which can be also combined together. And at this point, we are going to switch to the live coding. So let's hope that everything is working as I have prepared. So I will be using Grid platform, which which allows me to easily create session of any configuration I want. So I have already 2 running for this case, but you can see, just for illustration, you can decide which GPU, which machine you want to. You have also pricing, and then just start it. By default, if I take it as a session, so I'm running Jupyter Lab and preparing and having the code session. So just to be clear that I don't cheat, so I will shut down all kernels and I will reset all outputs. So you will see that everything should be real. Yeah, also this code can be found in this repository, which we share with you later. But let's start with the beginning. So we are installing PyTorch Lightning, and nowadays torch metrics are included inside. You don't need to install them separately. Let's hope that it works. Okay, so let's stop it. Okay. Shut down kernel. Connect to kernel. Okay, so I will run it all and will comment it as it goes, but you saw that I was removing all the outputs, so it should be correct. So I'm installing the PyTorch Lightning. I just put there printing what the PyTorch version and eventually Kaggle because it was I'm using. So it's PyTorch Lightning 1.510. Then we are also using Torch 1.10.2. We are using, we have connected to T4 graphic cards, which is quite nice and reasonable price. Then I usually suggest, or always suggest that when you are starting any machine learning task, you should always know what your data. You should get a hands on your data. You shouldn't start just learning and just playing with the models and hope that it will give you what you expect. So first, what we will do is short dive to the data set. So to see what are the annotation distribution, how the images approximately look like, and so on. So with this Kaggle data set, so we have the coordinate file and the train.csv, which includes image name and labels. And we see that the labels, as is multi-label, it's still stored in single column, but separated with space. So this has 1 label, this has 3 labels, 1 label, 1 label, 1 label. But what are the, so that's interesting also how many labels are is in combination. So we see that most of the images include just 1 label. Some include, it seems like 1/10 of the data set, 2 labels, and really minimal includes 3 labels. What are the label distribution? So if we take all the labels in the data set and put them one by next to each other, in row, so we can compute simple statistics. So we see that the most of the data set is scrap, the minimal is powdery middle. So eventually we can also consider to apply some balancing to the data set, because most of the machine learning methods assumes that the data or the labels are approximately same appear same proportion in the data set. So, and I think, as I remember, it was a mistake of several other competitors in that challenge that they were considering it still as a single label. So for them, it was that this combination of labels was in the end one label. So then for them, the task was image classification for single label one of 10 different classes. In fact, it should be multi-label classification one of 6. So when we have the images, so let's randomly take a few of them and
Jirka,
just hi.
sorry to interrupt. We have someone in the chat asking if
Okay,
we could increase the screen resolution or the font size. Can we do that? Maybe the font size is easier.
I'm not sure if font
All right.
size, but
Yeah,
is it
I
better?
think it's okay now. Thank you.
Okay. Okay, so when I was about, yeah, so just showing the images from the data set. So we have, yeah, so we are grouping those, so we are reading the config file, then grouping by labels, and then showing what images we have. This is the association with the, let's say, combination of labels. This is not the correct one, how it should be solved, but you see what's the proportion of number of classes. So there are just 120 of fish eye leaf and rust together. And this was just for me to computing dataset color mean and color STD. So now coming to the lightning, when we know something about the images and something about the labels. So PyTorch Lightning is still working with all the PyTorch primitives. So we are going to define a standard PyTorch dataset. Then we are going to use PyTorch Lightning data module, which is aggregating the information about your data. Then we will defining a Lightning module, and in the end we will train it. Well, completely at the end we will use also some inference to show you. So the standard data set, so we need to define, we have a set of folder with images, we have a file, when we know the mapping between labels and images. So what we are going to do here, we just save the dataset folder. Eventually, if we have any transformation which is useful for augmentation and increasing the model robustness, so it doesn't overfit for 1 pixel or anything like that. Usually the augmentation would be, let's say, shifting, rotation, vertical, horizontal flip, and so on. In this case, I was trying to make it another general, so the input could be already a data frame from pandas, or it can be just a string to a CSV file, so it's loaded afterwards. Then for some optimization on the speed, so I was expecting that if someone gives me all the unique labels, I don't need to compute them again, but probably it's not worth in this moment. Then I need to save some lookup table, because for the classification, we are going to have output, which is 6 different six different neurons. And then I need to know or keep in mind which kind of neuron, which is in the maximum, is mapping to what string label. Then we count just number of labels for getting the number of heads or the final neurons in the final layer. And yeah, I think we can skip this part. This is just for later, let's say, formatting the numerical labels to string labels. Label histogram, I think we don't need either. And then the key part of the data set, as for any PyTorch dataset, is get item. When we are asking for index in the dataset, and we expect to get image and a label. So we have loading the image as it is, over here. Then we have the labels, so we ask for the label. And if we have defined transformation, so the transformation is applied on the dataset side. Then we have here kind of soft label, because as we use the same dataset also for testing, and for testing we don't know the label, so we don't want to fail it. And yeah, this is about it. So this could be also skipped. So then we create our dataset. And what I usually do is putting some sanity checks at every step. I create some, some part of my code base. So at this moment, I want to check that I can iterate over my dataset. So when I ask, give me a sample, which means pair image and label, that I get something what I expect. So you see that I'm just creating the dataset, taking first 9 samples from the dataset, and I'm just simply plotting the image and showing the label as a title. So that's something which I would expect. So I have a picture of a leaf, and at the top I have a tensor of size of 6, when the ones represents that the particular label is present in the picture. 0 is that it's missing. Then now coming to the Lightning data module. So you see we are inheriting from Lightning data module. And at this point, we need to connect multiple datasets together. So we need to have training dataset, validation dataset, and eventually test dataset. Here we just pass all the input variables to the module. Then Lightning data module has a few optional and few mandatory steps, few methods. So you can define also prepare data, which is, for example, if you need to download data from server and it's usually done on the main device, then you define setup, which is called on the device which you are using. So in our case, we are doing the split between validation and training, as the input dataset contains only validation images. And I can show you over here. So we have data stores, which we connected, and we have folder with train images and test images. So in our scenario, we will be splitting the train images between really training images and validation images, which I have set here. So I have defined a proportional split between training and validation, and I will take the portion of training data for it. So this is about the setup. So defining the unique labels, just in case that because there is kind of extreme case, if I would be taking too small validation data set, and which may be missing one of those labels. So the size of the outputting tensor wouldn't be 6, but would be, for example, 5 or 4. So this is just ensure that I have all both datasets validation and training as the same. Eventually, I think you can also use some PyTorch dataset subset, which would work also in this case. So we are listing images, then we are creating, this is the dataset class, which we are defining over here. So we are using this dataset class, passing all the attributes, set train on validation, because in the previous one, we have defined that we are splitting the dataset, that the split is between 0, 1. And if we say that it's train, so I take the first half. If it's validation, I take the second half. Well, second portion, it's not half, but yeah. So we have the images and saving the training dataset and validation dataset. Then the required methods for the training is that Lightning expects training data loader, validation data loader, and optionally test data loader. Here we use, again, standard PyTorch data loader. We pass the dataset, we set what's the batch size, a number of workers which are processing the images. So it's good to, I usually recommend to set the same number or very close number to number of cores or CPU cores. But on the other hand, you should be aware that each of those would take some amount of memory. So you may get to breaking your machine or fouling your computer because it will take too much RAM, more than you have. So here we are defining some basic augmentation. So usually for the validation, you try to keep it the same. So we do just resizing for the inputs head, input model, then crop. Well, I do the resize a bit larger because some images are landscape, some are portrait. So just to be on the safe side, so I take 250, then crop it to 220 as it is for most of the smaller modules, the standard input receptive field size, then convert it to tensor and normalize it. As I'm using pre-train, I will be using pre-train ResNet. So it's pre-trained on ImageNet. So those are color means and validation from the ResNet. Eventually, as I had before commented out, you can also compute your color mean and color STD for this particular data set. And as before for the data set, so I'm going small sanity check that I create the data module, which is taking the CSV file, set the base data path to this folder, then using training and validation transform. Split is 90%, 10%. Usually it's recommended to have bigger validation, but this data set is rather small, so let's keep it this way, 6 cores. And now I'm taking the validation data loader, iterating over the validation data loader, which should be giving me batch of images. So you see that now I'm also iterating per each example or per each input and also output, because I should be getting image and label from each batch and see what I get. So you see that those images are rather different, but that's also because of the visualization. As I'm normalizing the color, the input image to those mean and STD, so then the color is shifted around 0 and the matplotlib doesn't show much around for the negative values. So now finally coming to the Lightning module. So I'm overwriting the standard ResNet architecture from Torch Vision, which I have over here. And what I'm doing that I'm taking the model and replacing the final fully connected layer, which is on the pre-trained model for 1000. So I don't need 1000. So I'm replacing it with a linear layer of 6 and defining the forward path that it's going through the model. So going from to the Lightning module, which includes the init. So it's so in the initialization, I allow to pass any NN module, or I will fill it with my lit ResNet. Then I save some additional information and define that I want to measure F1 score for this data set, as I think that it's a well balanced metric for most of the cases, as it's a combination of accuracy and precision. So for the forward, I'm using sigmoid as it is multi-label classification. Then as a computational loss, I will be using binary cross entropy weight logits. Again, that's because of its multi-label loss, multi-label classification problem. So when I have the training step, so the badge is already on the device, so I don't need to care about it. So I just know that my badge is, each item in the badge is composed from image and label. So I'm passing the image to the model, getting some predictions, computing loss between the predictions and true output, which I want to obtain, and logging training loss, and also logging training F1 score. Very similar, just don't return the loss. Is also for validation steps. So I'm passing through the model, computing loss for validate as a validation loss, and logging it to the output. Then I defined optimizer as Adam weighted with learning rate, which I define in the init over here, learning rate, and some cosine annealing scheduler. So now I'm creating simple model and passing it to the Lightning module. And now we come to the training. So we've been talking about the data and model, and that's pretty much all what we need to care about. So in this training with the Lightning, so everything after is handled by the trainer. So we just define some additional components. So for notebooks, I usually use CSV logger, as it is rather easy to include the final metrics inside the notebook. Then I also, as a bit advanced thing, I can use stochastic weight averaging callback, which is useful for improving the model performance. Then I define checkpointing, and which is important, especially for larger models when each epoch can take hours. So you want to always save the best model at the time when you reach it. You don't want to save only the last model. So in this moment, we are saving according validation F1 score and using the name in the name. So later on, we may have saved the models in the log file, and then by the name we will know which one was really the best, and we are optimizing for validation F1 score as the best one, as the maximum. So for the trainer, we said that we run on one GPU, we add our callbacks for the checkpointing and stochastic weight averaging. We use our CSV logger, we just train it for 10 epochs. That we use mixed precision just to, which allows us to use bigger batch size as it takes less space in the memory. I'm not really using this part about auto finder, as I have commented later on, but I can easily just accumulate gradient, which is also not trivial if you do it on your own. So you need to keep in mind when to reset and when not to reset, and run the training. So let's hope. Oh, so fine. I have the training is finished after 10 epochs, and the final loss is about 0.6. F1 score on the training is 84%. Validation is 88. So it seems that we are probably not much overfitting the training data. So just taking the saved metrics from the logger, just loading and aggregating over epoch. So I don't want to show all the numbers there, as there is a step, epoch, and those. So I will be showing only training cost and validation. So we see that it's going very well. Maybe there's something missing, but yeah, we see that at least the validation loss is going down. So it's learning something, and obviously it's learning in good direction, because also the F1 score is going up to 88. And I feel that it would be probably just the visualization issue of that one, because we saw the numbers over here. So we have the numbers in the log file. So let's continue further. So if you go to the prediction, so we have the test data loader. So the same as we showed with the validation before. And now when we have the model, so we just we don't need to compute the gradient, as it is prediction. So we don't learn anything anymore. We set it as an evaluation mode. This is the manual way how we do it. So then we would be going through the test data set, which doesn't have the labels. So then the second, as we introduce it at the beginning in the dataset part, so if I don't have labels, so I will be using the image name. So at this moment, I am getting, instead of the label, I am getting the image name, so I can pair it back to in the prediction time. And this is if I iterate it over just a few examples, I think that the train data set is very small, so that's the reason. It just includes 3 images. So we are getting numbers, which is numbers how likely it's that the particle label is in that image, and then later we pair it with the text predictions. So the second label is frog eye leaf spot. The first label is complex, and the last one is crab. And saving it as a prediction CSV file, which is uploaded to Kaggle for your competition. But also there's one extra thing that you cannot, well, it would take quite a long time. Well, you would need to always train the model on the Kaggle, right? Because it needs to be submitted from the kernel. But what you can do, you can train the model on your any device like I'm doing here in this session, and then just upload the model to your dataset, kind of storage on Kaggle, and then load it there and run just the inference. So here we have our checkpoint. So we have passed to our best model in the checkpoints according to the F1 score, which is loaded. And then I do pretty much the same as I did before. So I initialize it. Well, I have loaded the path. Now initialize the model from the loaded checkpoint, and then run the predictions. So now I show just the numbers, but also you can do the same pairing with the labels, in textual labels. So this is about Lightning itself, but then there's also, we have PyTorch Lightning Flash. Let me, if I can, okay, I cannot move it. So let's, yeah, so I will do the same here. So I will shut down kernel. I will remove all outputs and run it here for you. So it's authentical. And so Lightning Flash is, let's say, another level of abstraction for Lightning. So it's very useful for someone who wants wants a very fast baseline and doesn't need to care too much about the implementation details. So this is very handy to have the Flash, because in few lines of code you are able to get baseline, very suitable baseline for image classification, NLP task, for embedding. Just about this winter I've been using Flash for 3 competitions, and for 2 of them I'm still at the top rank, and just using Flash without any other special hacks yet. So maybe I will apply some later, but at this moment I'm quite satisfied with the score. So I will be using a different graphic card, because I will be using also a bit bigger model. So using V100. And yeah, this is exactly the same what we had before. So we just load the model, load the data, then see what are the label distribution. That's copy paste from the previous one. And now we are coming to the Flash part. So we are just loading from Flash image classifier and image data data for the image classifier. To load the data, we can load it from CSV, or as I have already done the analysis before, so I have it loaded with the pandas data frame. So I defined that the images are saved in a column named image. Then I have the labels separated by space, so it's multi-label task in column labels. This is my loaded data frame. My images are saved in path to the dataset /training images. as I will be using EfficientNet later on, which has a different receptive field. So I will using adjust it to this model. So it will be 384. Use batch size 8, workers 8, validation 0.2 split. And what's handy about most of them, most of models for Flash, they have wider integrations with other libraries. So for example, here you can use, I believe, all modules from TIM, which is one of the, it's still implementing state-of-the-art methods. So you can easily take just EfficientNet with head before. You will be using optimizer Adam weighted. You can also pass additional optimizer arguments if you want. Learning rate, some reasonable number. It's a guess at this moment. And then define the labels and multi-label task. Then the only thing which is remaining, so we covered pretty much what we were spending before for about half an hour. So we can describe here in just eventually 2 lines of code, as it is separated to multiple, but still could be easily just 2 lines of code. And then running training. The trainer from Flash is just a light wrapper to the Lightning trainer. So you see that all the arguments here are the same, and you can also use all the callbacks from PyTorch Lightning. So we are defining to train it on 1 GPU card. Again, just using CSV logger for this notebook, as it is easier for visualization. Using mixed precision, we will be validating every half epoch. And yeah, refresh progress bar at 1. It's just kind of handy thing. And what we are using here is a freeze unfreeze strategy. Well, you can use freeze, which is training just ahead. You can use unfreeze, which is training everything. But usually it's better practice to use some freeze unfreeze when you first adjust your head to number of labels and some, let's say, better than a random distribution of weights. And then after you unfreeze it, so you run the full training, you update all the weights in the model. And at the end, we just save it with the checkpoint. So let's see if it's still, yeah, it's still training. So we are at about epoch 1. We have approximately same loss as we had with our model, well, double, but still at first epoch as we had with my previous model with ResNet 50. And the training is okay. So let me see. There should be also epoch. So for the previous epoch, we have training 0, 70, 78, 79%. And validation was already 88. So we were almost on the same numbers as we've been seeing here. We ended up with train validation 84, also just for 5 epochs, and validation 88. So, but don't take it that it's different framework. I would say that it's more also about the model we are using, as here we use EfficientNet before, and this model is using ResNet 50. And yeah, so we are still training, and at the end we would be showing the learning curve. So I think that at this moment we can jump to questions and then check the results of this model later on.
Yep.
So, I may have last slide here. So it's what I just went through. Demo with PyTorch Lightning, demo with Flash, and maybe quick recap. So what are my kind of personal suggestions is that when you try to solve any machine learning or deep learning task, you should first understand what the data are about and what task you are solving. As for example, for this plant pathology, there were many people who were trying to solve it as a single label classification. In fact, it was multi-label classification. And for us, just using the proper task gave us, like, I think 10 or 15% boost above everyone else in the competition. then start with strong baseline. So I think it's very reasonable to play with Flash, as you can really easily go and find, well, iterate over multiple models. So you can have a simple loop and check was efficient in B4, B5, anything, how they perform, and share your progress with your colleagues on GitHub, Medium, or anything. Yeah, and keeping the stage for you.
Yeah, so thank you, Jirka, for showing us how we can use PyTorch Lightning. And while it is still training, we can address some of the questions from the audience. So I'll start with this one. Does PyTorch Lightning provide out-of-the-box modules to deploy models? What MLOps platform would you say synergizes best with PyTorch Lightning for the purpose of a real-world ML application?
Well, PyTorch Lightning doesn't give you any models out of the box. PyTorch Lightning, as I mentioned in the beginning, is rather seen as a proper code organization and removing all the boilerplate from the training loop. So it doesn't give you any model. That's the stage for Lightning Flash, as I showed. So you can also easily just load any model from Tim by the name and run the training for, let's say, ResNet 150 or EfficientNet or Vision Transformers. All of those models from a Tim codebase or Torch Vision are out of the box for the Flash, but not for PyTorch Lightning. Then, as you were asking about the platform for Devops, so I'm using Grid platform, which is nice that you can easily define your machine which you want to use, and just by the resources you need. You don't need to remember, for example, for AVS, the names of the machines and then details, and so you have everything at the same place. So you know that you want to use 8 T4 cards with almost 400 gigabyte of RAM memory, and it will cost you $8 per hour. And you create the session and you can run anything you want. Then regarding maybe the fast iteration, as I will be sharing later to you this series of blog posts. So we have here also one blog post which is related to hyperparameter search. So this notebook, any of them can be very easily converted to Python script, right? So we just kind of copy paste the, for Flash, it's just copy paste this few lines of code, how you create your model, how you train it, and how you create your data. For Lightning, you would need to copy paste more code. So you have your class definition and then how you put it together. But as you have it just one single script, so you can run hyperparameter search with Grid platform, which has nice feature that out of the box, you don't need to, well, it's enough when you have just Python script, which accepts some command line arguments. So you can iterate on your, and Lightning has CLI, so also helps much simplifies your work there. So I can maybe dive there later if you want, but just for simplicity, keep it. So you can iterate, for example, with Lightning over several recent architectures, over multiple learning rates, and then you connect your data store. So you have it using the same data for everything. You don't need to download it in each script and for some number of epochs, and then it's spinning out as many configurations as you have, that the same number of machines. So all are running in parallel, and from all, as a PyTorch Lightning by default is using TensorBoard. So this platform is aggregating the results from all machines which are running from the tensor boards and aggregating together. So you can, in a real time, watching what's your training performance. So if you find that some models are not performing very well, so you can kill them sooner. And what I like about this platform is that you can easily run spot instances. You don't need to care much about how to do it or what you are going to do. You just check that you want spot instances, which are rather cheap for any platform like AWS, GCP, Azure. Like the saving is about 80%. So I was running this experimentation, which takes about half an hour for how many? 3 times 3, 9 configurations, and it cost me about $1 or $2. So that was my choice.
All right, thank you. And moving on to a different question, we have Luis that asks, sometimes loading a lot of the images to RAM is unfeasible. I saw you mention something about it, but can you explain again how does PyTorch Lightning handles these cases?
Yeah, well, I think that there are two things. One is that well, in most cases, there is really no need to load all the images to the memory. I mean, like all data set. That's maybe to clarify. So you most likely never will be loading all data set to the memory. It would be faster, but it's not necessary. Then the second part is that what I was doing also for this competition, you should decide what are the reasonable size of your images. Because, for example, for this competition, the organizers provided 4K images, but in the end, if you are using most of the standard models, so the receptive field is up to 4, at most 500 pixels. So you would be doing the downscaling for each epoch, for each image, which was taking quite a lot of time. So I had the original work on running on Kaggle, and one epoch took me about 1.5 2 hours, just because I need to do the downscaling for each epoch. Then I was, let's say, doing it offline, downscaling this data set to just 600 pixels, so still have reasonable margin for any augmentation. And then I was able to run the same training procedure, not with 4K, but with 60 pixel images in 10 minutes. So it's again, like, you should understand what's your data. So there's no need to run everything on the full scale if you are using small model, right?
Yep. Okay, thank you, Jirka. And we have another question from Luis. And it's more like of a general question, and he asks, do you have any tips and tricks for debugging a deep learning model with PyTorch Lightning?
Tips and tricks. I think that a good feature, not sure if I have it shown here, is using fast def flag in the training. Yeah, I used to have it here. So you don't need to run the full training if you are not sure if everything is correct. So you can just run this fast def tool, which is, I think we have it finished here, everything, so I can show it. It's evaluating that everything is running as expected. So, and it's taking 2 epochs. Or that's for, let's say, validating that your pipeline is correct. Then another thing which you can use, it's also beneficial, is overfitting to small number of batches. And that's a sanity check for your model that it's able to learn on the given task. And in principle, it should be overfitting. Well, you should see that the training loss is decreasing significantly, and eventually some metrics on the training data set is also increasing significantly. For sure, it won't work on the validation because you are trying to overfit just to small amount of data.
So you just need to add that parameter, and you don't need to change your data loader. Yeah. It will choose some random small number of batches. Yeah. All right.
Exactly.
Okay. I don't know if you want to share anything else, Yuka, but
I think we have finished the training over here with the Flash. Yeah. So we see that with the default augmentation for that task, it's probably not sufficient, as you see that the training loss is decreasing, but the validation is kind of saturated on some 0.1. Similar is the same, similar for the F1 score. So the training is going up to almost 100, but then the validation is saturated around 0.9. So I would guess that we are overfitting the training data, and some more augmentation should be added, which can be also very easily done with the with the Flash integration.
All right, and I think I have one final question. What are like the major features of PyTorch Lightning that you enjoy the most and that you would recommend for practitioners to use?
I think that all are interesting. I think that is more rather question like what task you are trying to solve. But for me, I like very much the mixed precision because it's really improving the size of batch, which I can use for each iteration. And usually the batch size is rather important for generalization. Doesn't apply always, but in most cases. Then there is the aggregation, which is also improving, let's say, the gradient is rather robust, so it doesn't oscillate too much, at least from my experience. And then easily plugging any callbacks. So you can also define your own callbacks to improve any process.
Yeah, and I can say that that's one of the features that I really enjoy about PyTorch Lightning is the flexibility of that you can have to implement your own classes, but you already have the base classes and all the hooks.
Yeah,
So
and you can
that
easily
makes,
switch between. You can easily switch between, let's say, tasks. So you can have task for, let's say, image classification. Then you would have on a cats and dogs, and then so you have your task, and then you can switch it with different data module. Or on the other way around, you have one data module, and you can apply multiple tasks on it. So it's very reusable, and then also very easily to share with anyone because anyone who would be using it, so he knows that you are using Lightning data module, which has certain methods which has to be defined, like the training data loader, validation data loader, setup and preprocess. And then when you are kind of following his thoughts, so you know where to look for it, compared to when you have everything written on your own. So it's kind of looking involved.
Yeah, that's really nice. And also like there's a lot of developments and new features coming up.
Yeah.
So that's always exciting.
Yeah, we are going to have next release will be next week with 1.6.
Looking forward to it.
Yeah, us too.
Okay, so thank you so much, Jirka, for the presentation and for showing us how we can use PyTorch Lightning. We really enjoyed it. Yeah, and thank you for everyone that watched. Please fill out our feedback form that's in the video description so that we can improve our events. And I guess I see you in 2 weeks. Thank you so much, Jirka.
Thank you for having me.
Bye-bye.
Have a nice evening. Bye.
Bye.